So we've been working with these logarithmic expressions, equations, functions for a couple sections now. One of the tools that we're going to be using is the idea of evaluating logarithmic expressions. We've also solved logarithmic equations. So we're going to use those ideas and transform them into something that we call properties of logarithms. We've done properties of exponents. That's something that you guys have definitely seen in Algebra 1, and we kind of use that to apply those properties into the exponential functions. So now we're going to learn the properties of logarithms. They're similar to the properties of exponents. They come from the properties of exponents. They're a little trickier. So we're going to walk you through these properties. There are 3 of them. So starting with the product property. Product property works like this. And I'll write it down and then kind of walk you through why exactly it works. So if we have log base x, whatever the x is, of a times b. So if there's a product, a times b, inside of your log function, you can write it like this. Log base x of a plus log base x of b. The reason that works, remember the way that our exponent properties work. Our exponents say if we're multiplying a base times a base with different powers, you add their powers together. And so since logarithms work the opposite way that exponents do, this says if you've got a product, you can split it up and you can add. But like I said, I'm going to do kind of a little mini proof, not a geometry proof, but just a way to show that this property actually is true. Okay? So our little proof, don't let the word proof freak you out. It's not like a geometry proof. We're going to say let b to the x equal a and b to the y equals c. All right, so the same base raised to different powers, we're going to have them equal to each other. So this means if we write them in log form, so if we write this one in log form, log base b of a equals x. And if we write this one in log form, that means log base b of c equals y. Okay, so we started out by saying, let b to the x equal a, let b to the y equal c, and then we rewrote them into their log forms. Okay, so that's where we're at so far. We've just kind of defined 2 different variables and then written them in log form. Okay, so what we're going to do is show what happens when you multiply these 2 together. Okay, so b to the x times b to the y. First of all, if we're using these expressions right here, b to the x is a times and b to the y is c. So that's what we've got so far. However, on this side, we know the way our properties of exponents work. So we can use our properties of exponents and say, all right, if I've got a base to a power times a base to a power, I add them. So b to the x plus y, and that's still going to be equal to a times c. My right-hand side didn't change at all. Okay, so now what I do is I take the log of both sides. All right, and this is just using that property of equality. We've shown before that if these 2 things are equal, their logs would be equal. Okay, so we can take log base b of b to the x plus y equals log base b of a times c. I should probably have a little times in there. Okay, so now, last thing, and this is the part that's a little bit tricky. We talked a couple sections ago about how exponential functions and logarithmic functions are inverses of each other. So if 2 functions are inverses of each other, they cancel each other out. So this log function and this exponential function are going to cancel each other out, and all we're going to have left is an x plus y. Equals log base b of a times c. All right, this side didn't cancel out because I didn't have an exponential function inside. All right, so now finally, well, what's x? X is log base b of a. So let's rewrite this one more time. X is log base b of a, according to this line right here, plus y is log base b of c, and then equals log base b of a times c. Now I know I use different variables, but this is exactly what we have written up here. Okay, so if I've got the product inside of a log function, I can split it up as two separate logs that are added together, or vice versa. If I've got two separate logs with the same base that are added together, I can write it as one log with a product inside. Okay, so hopefully that proof wasn't too painful. We're going to use these properties on a couple of following examples. All right, so let's start with this. So we know that log base 4 of 2 is equal to 0.5. All right, we want to use that to approximate the value of 0.3. All right, so here's what we got. We know that 32 is 2 to the 5th power. Okay, so we are going to write log base 4 of 32. It is 2 to the 5th power, which means, now we're going to go back and talk about what exactly exponents mean. This means you're writing 2 times 2 times 2 times 2 times 2, 5 times, right? So if we can write it out like that, what that means is that we can use this property right here. If you've got a product on the inside, which we do right here, we have 5 of them, you can split them up into different pieces and add them together. So we can do log base 4 of 2 plus the next one, log base 4 of 2 plus the next one, log base 4 of 2 plus, and now we've got 3 of them, 2 more. Log base 4 of 2 plus log base 4 of 2. Okay, so I've got this whole strand that I'm adding all together just using this property. I'm kind of expanding upon that property. So each one of these is equal to 0.5. So I have 0.5, 5 times. I could also just multiply it by 5, but I'm trying to show you exactly how the property works. So this is 1, here's 1 again, and then this ends up being 2.5. All right, so it is approximately 2.5, log base 4 of 32. All right, now quotient property. Quotient property, we've got something that's very similar, and I'm not going to do the whole proof thing out again. I'm just going to give you the property, and you can look in the book. There is a full-out proof, just the way we did with the addition property. So the quotient property looks like this. If you have log base x of a divided by b. Okay, so what this one is, this one started with a product inside of a single log function, and you wrote it as the addition of 2 separate logs. This one starts off as a quotient, and if you could guess, I bet you'd probably think you'd split it up as subtraction of 2 separate logs. So a very, very similar property. A product inside one log becomes the sum of 2 separate logs. A quotient inside one log becomes the subtraction of 2 separate logs. All right, so a very, very similar property. Like I said, there is a proof, I guess, quote-unquote proof, just like I did right here, that you can find in the book for this one, if you are at all curious about it. All right, so let's flip over and look at some examples of that. Well, I guess first we are looking at the product property, and then we're going to use the quotient property. All right, so the power property looks like this. If you have log base x, and then you've got b raised to the power of m, all right, so b raised to some power, you can move that m out front as a coefficient. Okay, and I'm not going to prove this one to you, but I am going to show you our previous example that should make this make sense. So this says if you've got a power on the inside, you could just move the power out front and multiply it by the log. Look at this one right here. This is log base 4 of 2 to the 5th. So we wrote 32 as 2 to the 5th. I could have just moved this 5, put it out front, and done 5 times log base 4 of 2, aka 5 times 0.5, which I kind of did that out the long way here and ended up with this. I could have used that power property, and it kind of saves some time. It's a little bit shorter than doing that addition property out over and over and over again. All right, so this next example, we know this value. It's an approximate value here. We're going to use that to approximate the value of log base 3 of 49. Okay, so we've got the same base right here. They're both log base 3. We want to base it off of what we know. So it's kind of like, all right, how can we relate 49 back to 7? So let's take this property right here. Instead of 49, let's write 49 as 7 squared. All right, so think about that. Absorb it for a second. Make sure you're good with it. 49 is 7 squared, so that means log base 3 of 49 is the same as log base 3 of 7 squared. And according to this property right here, see how I've got an exponent right there and right there? That means I can move this exponent out fronts and multiply. So I can move the 2 out fronts and multiply by this right here, okay? And then I know what this is. So it's 2 times this approximate value. All right, and that's something that I would assume that you're just plugging right into your calculator. But we get about 3.5424 when you multiply that by 2. Okay, and you could always check these values. If you did plug that into your calculator, so this is saying 3 to what power gives me 49? Well, we know 49 isn't an even power of 3, which is why you get this crazy decimal here. All right, 3 to the third is 27, 3 to the fourth is 81. So that's why 49 falls somewhere in between a power of 3 and a power of 4. Okay, so our last little section here, we're going to use these properties to solve logarithmic equations. All right, so if you look through all of these properties right here, let's start with the left-hand side. The left-hand side you can fit with this property. So we're kind of going to go in reverse. If there's a number out front, like there is with the 2, you can actually move it inside as an exponent. So following that power property, I'm going to write my left-hand side as log base 7 of x squared. I'm just going to move that 2 onto the inside. Okay, and then equals, now this side right here, I can use my product property. And I'm going to put that on the screen too. My product property says if I have 2 separate bases, or 2 separate logs with the same base, that part's important, I can multiply the insides together and write it as a new log. So that's what I'm going to do right here. So log base 7 of, it is very important that they're both base 7, I can multiply 27 times 3. And 27 times 3 is 81. Okay, so I used some of my properties that we wrote down to kind of simplify these 2 sides, and now I'm going to go right back to what I was doing the other day. If I know they're both log base 7, what that means is that their insides must be equal to each other. If the left-hand side is equal to the right-hand side and they're both log base 7, it must mean that this x squared is equal to this 81. All right, so we solve by taking the square root. Remember what that means. When I take square roots, I always write a plus or minus. However, when we're talking about the domain of a logarithmic function, we're only allowed to plug positive numbers into a logarithmic function. So we don't count the negative version. We only count the positive version of 9. So negative 9 ends up being an extraneous solution. Positive 9 ends up working. So we only count the positive 9 with that. Again, because the domain of a log function is only positive numbers. So we couldn't have plugged in the negative 9 even if we wanted to. We would have gotten something that does not exist. Okay, last one right here. We're going to use some properties, very similar properties to what we just did right here. We've got the same base, base 6, so we can actually multiply these 2 things together. All right, so log base 6 of, and then I have got x times x plus 5. So basically, I'm just going to distribute the x. If I multiply this x times this x plus 5, I should have x times x, which is x squared, and then x times 5, which is 5x. Okay, and then this equals 2. Now, I saw 2 different equations, 2 different strategies that we're going to use. With this type of equation right here, they both had log. It was log base 7 on this side, log base 7 on this side, so I just set the inside pieces equal to each other. That's great if you have a log on both sides, but here you don't have a log on both sides. All right, so your technique is to write in exponential form. Okay, so I will say that again. If you do not have a log expression on both sides of the equation, you've got to write it in exponential form. Okay, so our base is 6. So we write 6 to the second power equals, and then this stuff right here, x squared plus 5x. Okay, so now we're going to keep simplifying. We're going to solve. This is a 36. So since this is a quadratic equation, remember you want to get just 0 on one side. So I have 0 equals, this is x squared plus 5x minus 36. So our main way to try to solve quadratic equations is to factor. So let's try to write this as 2 separate factors. Since this is an x squared, I know it's going to be x times x. And then for my constants that go right here, I'm trying to multiply to negative 36 and add to positive 5. The way I would do that is with a positive 9 and a negative 4. So you can always FOIL it out real quick, see if it works. Now if we solve these, if I take x plus 9 and set it equal to 0, I get negative 9. And if I take this x minus 4 and set it equal to 0, I'd add 4 to both sides and I get 4. Now remember the restricted domain of log functions. If I tried to plug in right here, log base 6 of negative 9, I am not allowed to plug negative numbers in. We just talked about that with the previous example. I'll remind you again, the domain is only positive numbers. So I can't plug in this negative 9. This 4, I'm good to go. I can plug that 4 in. So that is the only answer that I'm going to end up with. Okay, so that finishes up our properties. We've got just a couple sections left. We've got 7-6 and 7-7, so we are on our way.